So I'm going to start this next section a little bit differently, but we're going to be talking about oxidation and reduction reactions, and then there'll be separate segments on different methods of balancing oxidation and reduction reactions, or something we often call redox reaction. But to begin with, we're just going to talk about something called oxidation numbers. Okay, so if you look at FeCl3, and you ask yourself, what's the charge of iron, right? A lot of you have been figuring this out this last few weeks. That 3 that's there got there because the iron had a 3 plus charge. The chloride had a 1 minus charge, like that, okay? And so it took 3 chlorides to form with 1 iron to form the iron 3 chloride. These numbers are known as oxidation numbers. What they really reflect, so just to make it real simple, for monatomic ions, right? These numbers reflect electrons gained or lost. So iron, if you think about Fe3 plus, in order to have been formed, iron had to have lost 3 electrons. So I went from iron to iron 3 plus 3 electrons, like that. These are part of what was removed from here. So I have my reactants on the left side and my product on the right side. So we say iron went to have an oxidation number, or an oxidation state, of 3 because it lost 3 electrons. Now, the chlorine also has an oxidation number. As a monatomic ion, its oxidation number, and I'm just going to refer to it as the ON number, okay, that's -1. What does that mean? That means the chlorine gained an electron to become Cl-, to become the chloride ion. We could do the same thing with magnesium. Magnesium's charge is 2 plus. It's 2 plus because bromide is -1 and it took 2 of them, right? So that's going to be a 2 plus. So its oxidation number is 2. And bromide, Br minus, its oxidation number is -1. Okay, so oxidation number for monatomic ions is simply the number related to the number, is the charge, and is related to the numbers of electrons lost or gained. And you'll notice in this reaction, magnesium lost 2 electrons. That's why it's +2 charge. But the bromines, and there's 2 of them, right? They each gained an electron, which is the gaining of the electrons, which in this case came from the magnesium in the reaction that formed the magnesium bromide. Now, not everything has a negative or a positive oxidation number. Take, for example, O2. Overall, the charge is 0 in molecular oxygen. So that means the oxidation number for oxygen, it's probably should have picked a different symbol. This oxygen, I always do this to myself, by the way, has an oxidation number of 0. Because no matter how you divide 0 by 2, you're going to get 0 for each, right? Iron, elemental iron, has a charge of 0. So iron, Fe, has an oxidation number of 0. And here's what we generally assume, that pure elements have an oxidation number of 0. They're neutral in essence. They've neither gained electrons or lost electrons. Okay, so this is the idea of oxidation numbers. is that we have positive and negative charges which can be assigned to elements based on what their charge appears to be. Okay? Now, that charge is generally related to the number of electrons that are lost to make positive oxidation numbers, or the number of electrons that are gained to make negative oxidation numbers. Okay, so the next thing I want to look at is just this very simple reaction, and this sort of will illustrate why oxidation numbers are important. And a redox reaction is or an oxidation reduction reaction is a reaction where the oxidation numbers of the elements in the reactions change. And they change because there's electrons that are being transferred from one element to another. Okay, so this is a really simple reaction. It's one of my favorite for illustrating this point. Look at that and ask yourself, is the reaction balanced? Right? And intuitively, the first thing we do is we think about mass balance. So we're thinking about zinc and zinc. So I have one zinc on this side, and I have a zinc ion on this side. I have a silver ion on this side, and I have a silver ion on this side. But I think it probably bothers you a little bit when you look at this positive charge here and you see a 2 positive charge here. And in fact, this reaction is not balanced. And the way we balance it is by looking at the oxidation numbers of the elements and figuring out how many electrons it took for that reaction to happen. So the first thing I'm going to do in balancing this reaction is I'm going to separate out the two reactions that gave the change in oxidation numbers. And so one of those is going to be silver. Well, I'll start with zinc since that's first. Zinc, solid, right, making zinc 2+. And the other one is going to be Ag+, makes Ag solid. So to be clear, right, I separated the reactions where the oxidation numbers of elements changed. So I'm trying to identify like the components of the reaction that go together where I'm assuming the oxidation numbers change. And for this one, it's kind of obvious because zinc went from zinc 0 to zinc 2+. And in order to do that, it had to lose 2 electrons like this. And the basis of me saying it had to lose 2 electrons is if I add those two charges up, they come to 0, and this one has a 0 charge over here. The silver reaction, what I have to do is I have to assume that it gained an electron like this. And when it gained the electron, it made silver metal when it was gaining that electron. Okay, and again, the basis for we don't usually put 0 oxidation numbers, but I'm going to go ahead and stick it there. +1 and -1 makes 0. And that's the basis for me assigning the number of electrons to that reaction. Now, in later redox reactions, we're not always going to get to 0 because we're going to have charges, right? So I want to recognize, I'm just saying, I'm trying to make the charge on both sides of these reactions the same. Now, when I separate a reaction, a whole reaction, this is considered to be the whole reaction, into two separate reactions, these are known as half reactions. Now, so, and two halves make a whole. If something's oxidation number increases, that's called oxidation. So oxidation number increases. Generally, we refer to that as oxidation. And so that's first reaction is my oxidation half reaction. That's this guy here. Okay. The other half is known as the reduction reaction. So if the oxidation number decreases, then that's known as a reduction reaction. It's a reduction of the oxidation number. Okay, an increase in the oxidation number is considered to be an oxidation, and a decrease in the oxidation number is considered to be a reduction. And in every redox reaction, in every redox reaction, you always have one oxidation reaction coupled, is what we say, to a reduction reaction. Now, if you look at these two reactions, right, you'll notice that this one has 2 electrons on the right, and this one only has 1. So what we need to do to completely balance this electrons is make sure that the electrons that are lost by one are gained by the other, and in order to do that, I'm going to have to double the lower reaction. So I'll put a 2 here, and a 2 here, and a 2 here. And that'll make 2 electrons on the left here and 2 electrons on the right over there. And when I add these two half reactions together, well, that was a weird thing, hang on. When I add these two half reactions together, there we go, that's better. I'm going to be able to cancel the electrons that are on both sides. Now, rather than just do it like that, I wanted to show you how you can sort of visualize this thing going on. Now, these are aqueous, by the way, plus 2 electrons makes Zn2 plus 2Ag plus 2 electrons. And you'll notice that on this reaction that I have 2 electrons that are the same as the 2 electrons over here, so I cancel those out. And that leaves me with my balanced redox reaction. And the thing that maybe bothered you before is now been taken care of. When I'm looking at this, there's a +2 charge over here and a +2 charge over on this side. And so now, not only did I mass balance the equation, because this first reaction is more or less mass balanced the way it looks, I also charge balanced it for the number of electrons. And that's sort of the purpose of redox reaction balancing, is being able to make sure that we also balance the charges. I was about to move on and I realized there's probably one more thing that I want to do here. I'm going to write here that this is the oxidation half reaction, and this is reduction. And again, oxidation is loss of electrons, and reduction is gain of electrons by an element in the reaction. And there's a saying that we have. It says Leo says Ger, and it stands for lose electrons, oxidation, and then gain. And I guess you should spell Ger with an E. Gain electrons is reduction. Okay, so that's one way to remember it. Now, the next thing I'll show you is how we balance redox reactions, but I also need to show you how we calculate oxidation numbers. So I should say the next thing I want to show you is how to balance redox reactions, but it's also important that we understand how to calculate oxidation numbers. There's a set of rules for that, and that's what we'll cover next, and then we'll have separate videos on different ways of balancing redox reactions.